Okay, we've put in some work to figure out some properties of limits when they exist, right? Limits have to be unique. If a sequence converges, it has to be bounded. Now we're gonna do some arithmetic with limits. Okay, so how can we sort of combine sequences in some ways, and what can we say about the limits of these new sequences? Sequences and limits. All right. So here's a nice theorem that you may have encountered before, or maybe could guess is true. That when you combine sequences in certain ways, their limits behave in nice ways too. So let's set the scene here. So let's say that an and bn be sequences that converge to the limits L sub a and L sub b, respectively. Okay, so an converges to L sub a, bn converges to L sub b. Okay, so there's a bunch of statements that we can say. So one, if c is some real number here, then this new sequence, so I'm just building new sequences out of the ones we have and saying what their limits are. So this sequence here is all the same terms as an, but all of them are multiplied by c. So instead of a1, a2, a3, it's this constant c times a1, c times a2, c times a3, and so on, converges to c times the original limit, c times LA. Okay, so again, this is just stating that our limits for sequences, when you start combining them with things or start doing manipulating them in certain ways, they behave the way we hope they would behave, right? That's what I would hope would happen, is if I just multiply all the terms by a fixed constant, the limit just gets multiplied by that same constant. Okay, part 2 here. This is a new sequence, the sum. So what is this sequence? All the terms are just the sum of the corresponding terms in an and bn, meaning that the first term is a1 plus b1, the second term is a2 plus b2, and so on. Okay, this sequence converges to the sum of the limits. Right, makes sense. The sequence was built by adding together terms from the two sequences, so the limit we get by adding together the two limits. And we'll go on. We'll talk about multiplication, get an analogous result. We'll talk about division, get an analogous result as well. So I'll just list those here. So the sequence you build by multiplying terms, right? You have a1, b1 is the first term, then a2, b2 is the second, and so on, converges to the product of the limits. And the convergence part is part of this too, right? So it's not just, it's saying that, okay, I built this new sequence, it does converge because the original two converged, and we know the limit based on the limits of the original two sequences. And then fourth is division. So for division, as long as the limit for b is not 0, we can do this. So if L sub b is non-zero, then the quotient sequence, an over bn, right, which has these terms in it, is, I said limit of b not equal to 0. Sorry, that actually needs to be that bn is not equal to 0. Sorry about that. So let me just. Right, every single term in b has to be non-zero, otherwise you get an undefined fraction somewhere. This converges to limit a over limit b. Sorry, let me let me add again both. You don't want your limit to be 0 either. Okay, great. So these are the statements. So I'll prove some of them for you. So I'll do one certainly in this video, and then I'll leave some for you to do on your own, and for us to talk about as well. So let's prove one here. Okay, so we want to prove one. So just as a reminder, this is saying that the sequence CA sub n converges to C times the original limit, which was L sub A. All right, so here's just a bit of scratch, right, for our convergence proof. So what is it that we want? In the end, we're going to want something along the lines of, okay, the terms in the sequence, which are CAN, minus the desired limit, CLA, is less than epsilon. Right, that's what we're aiming for, right? General formula for the terms, or general description of the terms, minus the desired limit in absolute value is smaller than epsilon. But here, this is nice because we can pull out the C, we can factor out the C. So this becomes absolute value C times absolute value AN minus L sub A is less than epsilon. Okay, so the point is, because we know A sub n converges, we can make this as small as we want. As small as we want, or as small as we need, since AN converges to L sub A. So here, we already know a sequence converges, and we can use that to our advantage, because this difference between the terms and the limit, we can make as small, we can make as small as wanted or needed. So as long as I can sort of turn this into some statement about the difference between A sub n and the limit L sub A, that really helps us out. All I'm going to do is divide both sides by absolute value C. And we get that. One thing to note is I'm dividing here, so this is okay as long as C is not 0. Okay, so that's something I'm going to have to pay attention to when I'm actually proving something. But this is great. Like, once I can say, okay, like this bound on the absolute value of AN minus the limit LA, then that gives me something I can work with. Okay, so here's how the proof is going to go. All right. So I'm going to let epsilon be greater than 0. Okay. So remember, I talked about C being non-zero to do that division there. That's what I'm going to require here. So if C is non-zero, then absolute value C is positive. Oh, and sorry, I want to just add a little bit here. So if C is non-zero, absolute value of C is positive, and that means that epsilon divided by absolute value of C is positive. Okay. So now let's use the convergence of A sub n. So since A sub n converges to LA, there exists capital N such that if little n is greater than capital N, then we get absolute value of AN minus the limit is less than epsilon over absolute value C. So we're in the habit of writing an epsilon there, but really any positive number can go there. So because I know epsilon is greater than 0, absolute value of C is greater than 0 in this case, and epsilon over absolute value C is greater than 0, I'm using that expression, right, that number, sort of instead here as my bound for AN minus the limit. Again, the fact that AN converges means that we can literally put any positive number in this place, right, the last thing I just wrote down, and we can find a capital N that will make this work. Okay, so that's the positive number I'm choosing there. Okay, and it's important to still have epsilon defined. Like it sort of seems a little weird. It seems like, why do I not want to call this epsilon? But if we do that, then this, we're not going to get to the result we need at the very end. Okay. In this case, I'm just gonna multiply by absolute value c. So absolute value c times an minus the limit LA is less than epsilon. And this becomes, so I'm really just working backwards through my scratch work here. This becomes c a sub n minus c L sub a is less than epsilon. And here is where I needed epsilon, right? The statement is supposed to be that for any epsilon greater than 0, I can find capital N so that c times an is within epsilon of c times LA. Okay, and so I wanted an epsilon at this stage here, and that's why I used epsilon over absolute value c earlier. Okay, thus c a sub n, this sequence converges to c times the limit LA. I've only talked about the c non-zero case here, so let's go to c equals 0. There's not a whole lot to say, but we just want to make sure that we're doing this proof completely. All right, so we covered c equals c is non-zero. Proof continued. So if c is 0, then every term in the sequence is 0. Right? So then c an, whatever the sequence was to begin with, it's now just a whole bunch of zeros, and c times the original limit LA is also going to be 0. Okay, so for any epsilon greater than 0, we have CAN minus CLA in absolute value is equal to everything 0 here. Just 0 minus 0 in absolute value, which is 0, and that's certainly less than epsilon. So again, we get the convergence we wanted. So C a sub n converges to C times L sub a. All right. Great. So that's the end of our proof here. As an exercise, I'd like you to try proving statement 2. Right. So that's with the sum. So exercise 5 for this week, I believe. Prove 2, i.e. this sequence an plus bn converges to the sum of the limits. You want the triangle inequality here at some point. All right. Great, and we'll prove we'll look at some more of these other parts of this theorem in another video.